So we assume the following. So we initiated event cause frequencies for the reflux valve uh, failing close is 0.08 in a per year. Where did I get this data? This information have different sources, and these sources of information have to be evaluated. And then that evaluation, sometimes it is given in this assumption page or assumptions documentation that is presented to each member of the team when you're doing a layer protection analysis. But it's just an evaluation. It's just a first uh, numbers that comes at year. So these numbers should be challenged during the session, and if everybody is comfortable and the sources of these numbers are trustable, or you can trust them, so then you can use them. So try not to use them just because they are in that assumption page. So if you see that the 0.08, 10%, 8% of a time of a year, this valve is breaking or is not working or is failing close, well, if you're comfortable with that number, let's use it. Okay, so for now, that's as much as I'm going to talk about these ones. From now on, I'm just going to use the numbers, and because it's just an example to show you what's the methodology, what is the technique that we use. So also we have in the same way that we have frequency of equipment failures, we also have probabilities of failure on demand of safeguards. For example, what would be the probability of failure on demand of release valves? You can get them again from generic data, and they might be influenced by the service and maintenance and a lot of other factors that affect the reliability or the probability of failure on demand of pieces of equipment. In this case, we consider the relief valve a safeguard, so we will say it is 0.05 probability of failure on demand, so one failure in 20 demands. And also for the auto depressurizing valve, we didn't show in there, but that would be a safety instrumented system for which we the total ensemble, we're giving at the moment a 0.01. That would be a very high seal 1. Most of the people say that 0.01 is a seal 2. Me too. I would, when the risk is so high, or the risk reduction is high enough that is just in the limit of between seal 1 and seal 2, I will say this is a seal 2 valve or a seal 2 safety instrumented function, right? So initiated event causes, frequencies for the reflux pump failure, same story as, or same issues that I explained before for the reflux valve failing close, reflux pump failure 0.15. So we can see here that the pump is failing more often than the valve, than the reflux valve in there. And also we have probabilities of failure on demand of the spare pump, and of, for example, another trip or another high temperature alarm coming from the basic process control system that is independent, that we can use as an alarm. And then the other thing that we needed in order to do the calculations was the tolerable frequency. What is the company's tolerable frequency with respect to this severity? What was the severity? The possible loss of life when the column overpressure and loses containment. So that's how often the company, this is the number that how much the company tolerates this type of accident happening, 1 in 10,000. So questions: is there still unmitigated risk in this scenario? So after we have our initiated events, and that has certain frequency, and if I don't do anything, the frequency is too high with respect to what I can tolerate. So I put safeguards. So I have this auto start pump, and I have the high alarm, I have the auto depressurizing valve, I have the relief valve, and all those ones lowered my risk of having that accident, or having the likelihood of that unwanted event happening, right? Or having that unwanted event developing and becoming the consequence, or that severity of the consequence, it might become the loss of life that I don't want to. So I start creating my table, LOPA table. And this LOPA table, I have In first column, I have my initiated events or causes, and I list them, all of them. And remember, we're making the assumption at this moment that the pump and the valve don't fail at the same time, so each one is independent from each other. This applies to rare event approximations and applies also to double jeopardy rule. So the pump failing, we already have this frequency, initiated event frequency, which is a 0.15, and we don't have any protection layers at the moment. So what is the risk that is do we have too much risk here? Do we have too much open gap between what we tolerate and what we really have in our hands at the moment without any safeguards? So without having this other event that could reduce the likelihood of this unwanted event happening, going all the way and causing the loss of life. So in this case, the probability of failure of demand, I would put a 1 because I don't have any safeguards, and if I had something in there and I have a 1 there, this is a 100% failure. Probability of failure on demand 1 means 100%. So I have my frequency of my first scenario, I would say, right? So I have then the reflux pump valve failing closed has a frequency of 0.08. Again, no safeguard, so my equipment on the control total frequency of failure, that if I don't do anything, will be made will be compounded by the addition or the aggregation of the pump and the frequency of the pump failing and the frequency of the reflux failing close, and all this is looking into a period of 1 year. Okay, so our base is time is 1 year, so we look at the probabilities of how things fail in the period of 1 year. So we have our sum mitigated frequency. That's what there's no mitigation at the moment, but after we put the safeguard, we'll say that's our mitigating frequency. It is the addition of the two. So I have to divide, or I have TF, what I can tolerate, divided my MF, and that will give me a value. That value is if I were to put a safety implemented function in there, if we were to put only one safeguard, like a safety implemented function, what would be its required risk reduction? What would be its required probability of failure? What would be its required performance that it needs to have in order to cover this risk gap that I have there, this gap that is too much with respect with what I can tolerate. So if I divide my TF over MF, I would be, in order to don't have any risk in there, it should be equal to 1. But if it is not equal to 1, then I would say that this will be the number for a safeguard to have in order to reduce the risk to a tolerable level. And we know that we don't have to put exactly at this moment a safety implemented function. Let's see, because we already have this other safeguards. We already have the pressure safety valves, so let's use them, right? So let's see the next slide what happens. So now I'm adding my release valve. So we saw before that we have a risk reduction factor. This is our gap. We need to reduce this gap. We need to close, in order to close this gap completely and be in a tolerable place, we need to reduce 2,300 units. That's that factor that has to be taken into account, equivalent to having the probability of failure on demand of a safeguard of 0.00043. Right? So if I take the reciprocal of 0.00043, I will get 2,300. The same way that we saw the tables before. So I'm adding the release valve. When I add the release valve, at the moment, then what I have is the probability of failure on demand is not anymore a 1. So now I'm multiplying a frequency times a probability of failure. So you can think of these two things as two events. So first event happens with certain regularity, certain frequency, and the second event would be it fails every time that is demanded, it doesn't fail that often. It fails with a specific probability. So I'm multiplying a frequency times a probability, and you have to go a little bit into probability theory in order to find out that it's okay for now, as long as you understand what that means. Multiplying this frequency times this probability, and then at the end what you get is a frequency, and we call this frequency is a mitigating frequency. Mitigating because it's being mitigated, that frequency is being mitigated by the probability of failure. So now we have two events that have to happen. The pump has to fail, and the safeguard has to fail and not work, right? Otherwise the relief valve will take me to a safe place. That is assumption, and I hope that everybody makes the correct assumption in there to take you all the way to a safe place, right? So that goes for the design and calculation of these release valves. So I get a reduction on my frequency because now there are two events that have to happen, and they do the same thing with the pump, and I put in the probability of failure on demand, so I'll get that number. So by adding the two the same way I did before and doing the calculations TF over MF, then I get a different number. I get 0.0087, and that, if you take the reciprocal of that number, I get 115. So if I went from 2,300 to 115 risk reduction factor needed. In other ways, it will be translated to I still need to reduce the gap. How do I reduce the gaps? By adding safeguards, by adding other events that will stop this initiated mechanism, or this mechanism of getting in and developing in and becoming this unwanted event. I could still prevent by adding another safeguard. So later on we'll talk more about during the safeguard profiler. Also we'll talk about the bow tie, on which will represent safeguards that are used in order to prevent or this unwanted event from happening, or this hazardous event from happening, and then that we might use other type of safeguards that will help us into preventing or protecting the target, or that not allowing this target to be reached, meaning the target would be the person that might lose his life. We can do something else after the fact that there was an unwanted event happening. So we can still mitigate that in such a way that the person or the target can escape. So there are certain other safeguards that we can use, and we call them also safeguards, but these are safeguards that are after this initiated or unwanted event has happened. If we still have time to react, then we will be able to use some other safeguards. If it is an explosion, for example, well, there's not much that can be done. Usually after explosion there are no safeguards. If the target was there, it's gone. So we'll be able to study this more using the safeguard profiler. So in this case we went from 2,300 to 115. So we continue to look then for safeguard and to see what happens. So we saw there that we had a spare pump, and we can get this spare pump to work automatically, right? By convenience, right? So we put a pressure level, we put a safety relay, attach the pump when the pressure is low, because or some other way that we can find out that the main pump is not working, so that we can have that spare pump as a safeguard working in there. So this pump will work towards this initiated event pump breaking, but it will not work towards the reflux valve failing close. So I could also use another safeguard as long as it is independent from the main basic process control system that is working and interacting in order to keep all the parameters inside that design operating envelope, or intended design operating envelope. So I might add an additional independent temperature transmitter to pay attention to that temperature when the deviation happens and operations or the DCS system is not able anymore to cope or control the distillation column to keep it inside the operating envelope, then this element independently will try to warn the operator, for example, with an alarm, high alarm, and the operator should know that he has to go to the reboiler and stop the heating somehow. So as long as you can specify all that, and as long as the operator has time to react and go there and do that, that would be a good safeguard to take into consideration to reduce further the risk. So now we don't only have the PSV as a has to happen. That's the event PSV failure, or the failure on demand. Now we also have another event that has to happen in order for the progression of that towards the unwanted event. Now would have to be this temperature SafeGuard alarm has to fail. So what are the chances now? What are the probabilities that the PSV fails and that the temperature alarm fails? So how do we account for that? We multiply the two probabilities of failures of both of them, and of course the number is smaller and smaller all the time. And that's the way that we represent how we reduce the likelihood of that initiated event from developing all the way and becoming the unwanted event. So that's basically what this table is doing, and that's basically what we're building inside what we will be building inside SafeGuard Profiler. So we have our temperature, PSVs, spare pumps automatically now coming in. So I can start using them. For example, for the reflux pump failure, I still have my initiated event frequency. Now I had my relief valve in there. I added the auto start pump as a safeguard and added the high temperature alarm. And where did I get these probabilities of failure on demand? These again could be taken from generic data, and if you have planned data or facility information documented from the maintenance department, from the reliability department, those are the numbers that you have to use. Okay, so these numbers are somehow in there from generic data and accepted in industry, so these are the numbers that we're going to use. Someone might argue, for example, that this auto start spare pump has a 0.1. My argue say it might not be a 0.1, might be a 0.15. That's okay. If someone can prove that, or if someone can objectively or argumentatively bring information that the probability of failure is less than that, then it would be put in there. So you will use those numbers according to your evaluations and expertise in the matter. So now we have we multiply the initiated event frequency times the probability of failure of each of the safeguards, and we'll end up with a very small number, or we end up with the mitigating frequency with respect to that event. Remember, these are, suppose we're assuming independent events from one to the other one. So now we go to the reflux valve failing close. That's why I can use the same relief valve that I use for that, because I'm not expecting both of them to happen at the same time. So this relief valve will engage with respect to the valve. So I can use it independently. So now I can multiply also according to the rules of mathematics and probabilities. I can rules of probabilities. I can multiply 0.08 times 0.1, 0.05. Now I have not a situation, but I have this very small number here, and I have this 0.004 mitigated frequency. So now I can see that the frequency of this pump leading me to that unwanted event, it is very low because I have more safeguards and I have this small number here. So what layer protection analysis allows you to do also, or SafeGuard Profiler allows you to easily see these things now. This is a very simple scenario, but when we have a complex scenario, you will see right away which of this initiated event have the most contribution to your problem. What are the ones that are contributing more to that, the likelihood of that event happening? And you will see that in this case it is the reflux valve. So if I need to spend money with respect to finding another safeguard, I will try to find a safeguard that applies to the reflux valve, because the reflux pump it's already low enough. If I put another safeguard that affects the reflux pump, then this number could get smaller and smaller, but the reflux valve problem is still there. It's not moving. It is 0.004. That 4 is not getting smaller. So this one could go very low, spending money, and it will not be effective, right? So layer protection analysis, SafeGuard profiler will allow you to study these things and to take decisions, right? Decisions on uncertainty of what is happening here. So if I put another safeguard, I will try to look for a safeguard that goes towards the highest contributor of the initiated event frequency, right? So, or this event frequency that is influenced my own wanted event. At that moment, I will add then again, so I'm adding the mitigated frequencies, and I went from 115 to a 4.074. So at this moment, I can see right away that I don't need a safety instrument to function as such, right? It would be too much. Now is any other small safeguard will drive all the way this residual risk that I have here to when TF divided by MF equals to 1 or larger than 1. At that moment I say, well, I already have reduced my risk to a tolerable level. So how close to that tolerable line do you have to get? It depends on each facility. Each company has their own rules and policies on what to do when you arrive to this residual risk that is there. Do you accept that risk, or you keep driving that risk all the way to nothing? It depends on how the approach and policies and that each company has, right, with respect to what they're doing and with respect to safety. So now we have the reflux pump, we have the depressurizing valve. I think that we didn't talk about that one yet. I guess this company wants to drive all the way, no risk left over in there, not even that residual risk in there. Right, so we have the auto depressurizing valve, and it is added. We can add the auto depressurizing valve, and we drove the risk all the way to 1.15. And some people say, well, I don't want even the 0.15, or by reviewing the scenarios we can see, well, this auto depressurizing valve also applies to reflux pump, right? Because it's on the same side as the PSV, and if the PSV applies to them, I can see that this very well will reduce the pressure inside the column if either the reflux valve fails or the pump fails. So I can use also the pressurizing valve on this scenario, and then all my risk will go to or even go over the tolerable level. So I will have more risk reduction, or enough risk reduction, in order to drive all the risk out, not to have a gap. The reason why I put here the auto depressurizing valve at this moment was to show you that the 0.0075 stays there, and I drove down the highest contributor from the previous step on the LOPA table, layer protection analysis, and we can see now that it went from 4 to 1.15, and I can keep reviewing these numbers and drive them all the way to a number greater than 1. Hopefully not that much greater than 1, because otherwise I will be spending unnecessarily. So this is the way that layer protection analysis methodology works. I'm sure that we're going to find more complex scenarios than this simple one. This was, certain point of view, simplified just to give you the first idea of how layer protection analysis methodology works. What are the what is the functionality? What good things can you find out from doing this analysis?